Start our class. So in yesterday's session we have discussed all these parts. How cold dilute alkaline KMnO4 gives the products with the alkene molecules, and what is the stereochemistry of that particular reaction and what is the use of that reaction, everything was discussed. So in today's session we shall continue with the osmium tetroxide, a similar reagents which gives almost the similar type of the compounds also. So that first of all it is osmium tetroxide, hydroxylation with osmium tetroxide. So in this particular case, alkane molecule on reaction with the osmium tetroxide, in the presence of, you can take the sodium hydrogen sulfide or else sodium sulfide, or else you can just take the hydrogen peroxide, which gives diols. These diols are the cis diols or syn diols. It means that the reaction, in this reaction, osmium tetroxide molecule add both the OH groups to the alkene molecule from the same side. So we shall take some of the examples here. CH2, CH2. This is an alkene or ethene molecule. IUPAC name is ethene, common name is ethylene. So on reaction with the osmium tetroxide, it just gives this molecule CH2, CH2, oxygen, oxygen, osmium, and you can take the oxygen like this. Here people may get confused how this particular intermediate compound has been formed. It is very simple. You just see CH2 and CH2. Osmium tetroxide is having the shape like this. Okay, so that if this bond shifts over here, this bond will shift over here, and these electrons will go back to the osmium. So giving this type of this cyclic intermediate product compound. So this cyclic intermediate on reaction with the any of these reagents. So you just take the H2O2, we get the CH2, CH2, OH, OH. It is a ethylene glycol. Okay. So let us take another molecule. How this particular compound gives the product. Cyclic molecule, let us take. Cyclohexene with one methyl group here, and you just add osmium tetroxide and H2O2, and you will get the molecule like this. CH3. Both of these OH groups will be added to the double bonded carbon atom from the other side of this particular group. Though this is a syn addition, but osmium tetroxide preferably attacks from the back side, because to avoid the collision with this type of the methyl part. And now let us see the hydroxylation with another type of the reagent which almost gives the similar type of the products but with anti-addition. So hydroxylation, with H2O2 and formic acid. So alkanes, the products in this particular case are similar to the osmium tetroxide, but this particular reagent gives the anti-addition hydroxylation. So that's why I am not writing the complete story. I just write down the anti-addition or anti-hydroxylation. Means one OH group from the one side, the other OH group from the another side. We just take the one example, cyclopentene, and take H2O2 formic acid gives OH group here and the another OH group from the opposite side of the molecule. So it is an anti-addition. Next, hydroxylation with iodine, silver acetate. And in yesterday's class we had discussed that how these molecules are going to give the hydroxylation products. If you want, you can watch that video. So you just see. So in yesterday's session we had completely given the reagents and which molecules are giving the glycols, like cold dilute alkaline KMnO4, osmium tetroxide, H2O2 and iodine. And in this, except H2O2, rest of these reagents give the syn addition products. So we shall see that molecules now. So here CH double bond CH R dash just subject with the iodine in the presence of the silver acetate, and later this is the first step, and in the second step it has to be subject with the NaOH. So directly we get the glycols again. So the molecules which are having the two OH groups on the adjacent carbon atoms are simply named as the diols or glycols. Now let us see oxidation with acidic, another reagent, that is, I will write down here, oxidation with H plus KMnO4 or K2Cr2O7. Sometimes they mention, instead of the H plus, they may mention it as a hot KMnO4 or K2Cr2O7. Not only these two reagents, there are some other reagent which always gives the similar products like these reagents, what they are going to give along with the alkene molecules. Those are HiO4, or else you can take the lead acetate, CH3COO taken for lead. You just imagine that this is a different reagent, this is a different. Don't think that both to be used simultaneously. HiO4 periodic acid or lead acetate, or you can use the sodium periodate, NaIO4. So all these reagents, they give the same products with the alkene molecules. So that I am going to discuss here. You just see, if any CH2 group is present in any alkene, any of these reagents, I am going to write down H plus, KMnO4 or H plus, K2Cr2O7 or HiO4 or lead acetate, CH3COO taken for lead, or you take the NaIO4. So these reagents main purpose is they convert this double bond CH2 group to CO2. And if any alkene part is having this type of the group in the sense here, the double bonded carbon must have at least one hydrogen. Here two hydrogen atoms are present. So double bonded carbon with one hydrogen, this particular part in the presence of these reagents will be oxidized to its respective carboxylic acid. Okay. So, and one more thing is there, that what happens if the double bonded carbon is not at all having any hydrogens. In such cases, this reagent simply oxidizes this particular double bonded carbon atom to keto group. So generally question arises, sir, here if it is able to convert it to the keto group, then why not this particular part to the aldehyde group? Actually the product is aldehyde, but these are the strongest oxidizing agents. The moment aldehyde is formed, the aldehyde will be converted or oxidized to the carbon dioxide. So I will take a single example. So in that single example, you just able to find out the products, so that more examples are not necessary here. CH3, C, CH3, double bond, CH, CH, CH3, now double bond CH2. You can see, you can find out all type of the groups in this particular molecule. You just see here, this particular, this particular CH2 group will be converted to the carbon dioxide. So that this gives the carbon dioxide part. Here no hydrogen is there, double bonded carbon atom, so it will be converted to the keto group. Here hydrogen atom is there, it will be initially converted to the aldehyde, later to the carboxylic acid, and this particular part will be converted to the again keto group, as it is not having any hydrogens on it. So that now the products can easily be written very easily, that is CH3, C double bond O, CH3 plus, and here it is COOH, CO, CH3. So we can write the molecule like this: COOH, C double bond O, and CH3 plus this one will be converted to the carbon dioxide. So these are the products if you use any of these reagents what we have discussed just now. So now let's try to see the oxidation with the palladium chloride. Oxidation with the palladium chloride. So here palladium chloride oxidizes the alkenes to the carbonyl compounds. You just take the alkene subjected with the palladium chloride in the presence of the water and approximately 50 degrees centigrade, or else you can use the palladium with CuCl2. Palladium with CuCl2. So they may give this combination or they may give this combination. Palladium with cupric chloride, any combination, temperature is common over here. So it converts the alkenes to the carbonyl compounds. So let us see some examples here also. You just take ethene molecule. This ethene molecule, when subjected with this palladium chloride H2O, it will be converted to the CH3CHO aldehyde. But at the same time, if you take the CH3CH double bond CH2 in the same reagent, it gives the ketone part. This highly substituted carbon will be converted to the carbonyl part. Other carbon will be reduced to the CH3 part, so that you will get the CH3 C double bond O CH3. Means you are able to get the aldehyde with this type of the reagents only, but not with the substituted alkenes like propene. Now let us see the oxidation with the selenium dioxide. These are all specific reagents. So the use of this selenium dioxide is, it oxidizes the allylic position. It oxidizes allylic position to hydroxyl part. We shall take some examples here. CH2 double bond CH, CH2 CH3 and CH3 CH double bond CH, CH2 CH3. So now if you use the selenium dioxide in both the cases, generally doubt arises among the students that okay, there in first case no problem. Why? Because only one allylic position is there, but in the second molecule there are two allylic positions. Then in which allylic position will be oxidized? In this particular molecule there is no doubt that only one allylic position is there, that will be oxidized to the hydroxyl part. But if two are there, then imagine that more substituted allylic position will be oxidized. So that here we get the molecule CH3, CH double bond, CH, CHOH and CH3. These are the molecules. You take any type of the molecules, concept will be same. So OH group you will get it. Next, another oxidation part, that is hydroxylation. Hydroxylation using peroxy acids. So peroxy acids means peroxy carboxylic acids we are using in this particular examples reagent. So let us see what are the peroxy carboxylic acids. Generally, if you take acetic acid, I am taking only acetic acid here just to explain. This is the acetic acid. And what does it mean by peroxy? If any molecule is having the oxygen-oxygen single bond, such type of the bond is called the peroxy bond. So if you insert one more oxygen here, like CH3, C double bond O, OH. Now it is a acetic acid but having the peroxy bond. So it is called the peroxyacetic acid. Peroxyacetic acid. Similarly, the most efficient reagent usually we used in this particular type of the oxidation, this type of the oxidation reactions are not only peroxyacetic acid, two more reagents are there. Generally, if you take the benzoic acid like this is the normal benzoic acid, but if you take the one more oxygen, if you add CO3H, this is called the peroxybenzoic acid. This is normal benzoic acid. Okay. Similarly, if you put one chlorine here, here meta position, CO3H and chlorine. So this is called the metachloro perbenzoic acid. Instead of writing the peroxybenzoic acid, just it is shortcut perbenzoic acid. So in this particular molecule, in a shortcut we write MCPBA. So meta position is always represented with the small letter M, rest of the letters are capital letters, CPBA, MCPBA, that is metachloroperbenzoic acid. What is the use of these reagents and what is the use of this particular reaction? It is very simple that you take any alkene molecule, subject with any of these peroxy carboxylic acids. Then you will get the epoxide. If this epoxide is subjected to the any mineral acid in the presence of the water, that means aqueous mineral acid, then you will get the glycol. Glycol means it is also anti-glycol. means anti-addition reaction we can expect. So I will take some examples. What does it mean by epoxide and what are these remaining products? 1 minute, it got stuck. Yeah. You just take a molecule. This is a normal alkene representation. This alkene is subjected with the some peroxy acid, peroxycarboxylic acid. Okay. So in peroxycarboxylic acid means I will take the some general representation. I am not discussing the mechanism, just I am discussing the procedure. And here you take one of this oxygen and take this oxygen and put over here and disconnect this bond and connect that oxygen to the both of these carbon atoms. So that is named as the epoxide. It is a 3-membered cyclic ether. A 3-membered cyclic ether is named as the simply epoxide. So I will write down 3-membered cyclic ether is called as an epoxide. And when it is subjected with the, I said no H plus here, acid catalyst. So the lone pair of electrons over present in the oxygen atom attract this H plus ion, so that we get the molecule, intermediate molecules like this.